Hi everyone, let's continue with session 5.1. So we're going to learn about actually how to solve linear second order differential equation with constant coefficients. Okay, so constant coefficients means all the coefficients, they're not like function of x. We don't have x, we have constants. Okay. So that means because it's second order, we expect to see like a y prime prime plus b y prime plus c times y equal to 0. And because it's second order, we need two initial conditions to figure out the two degree of freedom, like the two constants c and d. Okay, so that's why we have the y of x0 is y0 and y prime of x0 is y prime of 0. Okay. But this is not in the standard form, right? So actually here, to solve second order linear differential equation with constant coefficients, you don't need to make it into standard form, okay? Just leave it the way it is. Okay, so when we have constant coefficients, actually we can expect the solution is gonna be exponential function. Why is that? I can tell you the example. The example from last chapter. Do you remember the population growth? We have dp dt equals to k times p. It's proportional, like the rate of change of the population is proportional to the population. So this is the same as saying, oh, p prime minus k times p equal to 0. So this is the first order linear ODE with constant coefficients. Okay, and what is the solution? The solution is p of 0 times e to the kt. So we have exponential functions. So that's why if we have constant coefficients, maybe we can think about maybe the solutions is going to be exponential. Okay, so a general form for exponential functions is a times e to the rx. Okay, so let's try to plug this in our ODE. Okay, we need y prime, so y prime is derivative of e to the rx is e to the rx times r, okay? And y double prime, so we have ar there, derivative of e to the rx is e to the rx times another r, so that will give us r squared. So, and then we plug this into our ODE. So y prime prime is ar squared e to the rx, and b plus b times y prime. Y prime is a times r e to the rx, plus c times y is a times e to the rx. Can you see all the terms consist of a times e to the rx? So let's factor out a times e to the rx. What do we get? Here we get a times r squared. The middle term we have b times r, and the third term we have c, okay? And we make it equal to 0 because a is not 0. We assume we have an exponential solution. So we should assume the coefficient a is not 0. Then if it's 0, then y equals 0. Yeah, we know y equals 0 is the trivial solution for it. Okay. And the exponential function is always positive. So the only way to make this equation to be equal to 0 is when a times r squared plus br plus c equals to 0. Okay, so we call this guy the characteristic equation. Okay, so this is a second order. This is a quadratic, right? This is a quadratic function. And how do we solve quadratic function? Well, we have the quadratic formula, right? It's 2a in the bottom, negative b plus or minus b squared minus 4ac. Okay, so, and depending on the discriminants, we have three cases. What are the discriminants? That is the things inside the square root. Okay, so when do we have two real different roots. So 2 distinct real roots. Okay, that is when the discriminant greater than 0. Okay, then we have 2 distinct roots. Let's call them R1 and R2. Then we actually get, we can decompose the quadratic factor in terms of a product of 2 linear factor. Okay, and in terms of the picture in the plane, okay, 2 real roots means the parabola cross the x-axis, right? Okay, next, repeated roots is when the discriminant is 0. Okay, i.e. we only have 1 real root, that is r. So let me call the real roots to be r1. So it looks like r minus r1 squared. Okay, and the picture is gonna be, you just touch the x-axis, so we have 1 x-intercept. So when do we have complex conjugate roots? So that is when the discriminant negative. In this case, we're not able to decompose the quadratic function in terms of a product of 2 linear factor with real coefficients. But however, we can decompose into a product of 2 linear factors with complex coefficients. So we expect to have 2 complex roots. No real roots, but 2 complex roots. They are, usually we denote alpha plus or minus beta I. Okay, alpha is the real part, beta I is the imaginary part. Okay, so in terms of the picture, it lies above the x-axis, so there's no x-intercepts. Okay, so here are the 3 cases. Let's talk about each case, and we will look at the examples from each case. First case, we have 2 distinct real roots, R1 and R2. Okay, so in this case, the general solution is going to be C1 times e to the R1. Because remember, we start with our solution is a e to the Rx, right? We get 2 roots, R1 and R2. So now we know that e to the R1x and e to the R2x are the solution, right? So a general solution is going to be a linear combination of those 2 solutions, right? Because we have second order, it means our solution space is going to be 2-dimensional. So 2-dimensional means we need 2 linear independent solution. Okay, so let's check whether these 2 solutions are linearly independent. How do we do that? We just said last time, we checked the Wronskian. The Wronskian for it is you first put down the 2 solution, e to the R1x and e to the R2x. The second row, you take the derivative of that. So that's why we have R1 e to the R1x, and then here we have R2 e to the R2x. Cross multiply. So this times this, subtract this times this. So we get e to the R1x times R2 e to the R2x minus R1 e to the R1x times e to the R2x. So you can see we can actually factor out e to the R1x and e to the R2x. We can combine them in the exponents. So we get e to the R1 plus R2 parentheses times x. And after we factor out this term, we get R2 minus R1. Okay? Because the exponential term is not equal to 0. Actually, it's greater than 0 for all x. And we also assume 2 distinct real roots. So R1 and R2, they are different. Okay, so that's why R2 minus R1 is not 0. So that's why the Wronskian is not 0. Okay, remember, if the Wronskian is not 0, then the functions are linearly independent. So we actually get 2 solutions, and they are linearly independent, so they generate the entire solution space of the differential equation. Okay, and then now, given any initial condition, y of x0 is y0, y prime of x0 is y prime 0, then we can solve this system, and we can get C1 and C2. Okay. All right. So that is the theory. How do we work on example? Okay, so don't worry, we're gonna do lots of examples in this video. Okay. So the first step, we know that the solution is let me use the black color. Okay, we know the we know the solution is gonna look like a times e to the rx, right? And then when you see, so to get the characteristic equations, characteristic equation, okay, whenever you see y prime prime, you put r squared. Whenever you see y prime, you put r, and whenever you see y, you just get constant. This is characteristic equation. Oh, why is that? Let's look at the last page. Okay, see? So see the last page. We have a y prime prime plus b y prime plus c y equal to 0. So the characteristic equation is whenever you see y prime prime, we place that by r squared. Whenever you see y prime, we place that by r. And when you see y, that's the constant term. Okay? All right, so we do the same thing here. Okay. All right. Okay, so let's continue. What is this guy? Wow, let's factor it. Are we able to factor it? Oops. All right. Okay, so we have 2r and r. Okay, 16. How do I get 16? We have 2 and 15 doesn't work. 3 and 10. Will 3 and 10 work? Oh, okay. So I can put 3 here. I can put 10 here. Then I have minus 10. This is minus 6. So we get minus 16r in the middle. Okay, good. So now this give us r is what? 10 over 2, which is 5. Oh, that is 5. The next one, we have r equals 3. See, we have 2 distinct roots. Then after we figure out the r, the solution is going to be c1 e to the r1. r1 is 5. X plus c2 e to the r3, 3x. This is my solution. Isn't it easy? You first, given the second order linear differential equation with constant coefficients, you first figure out the characteristic equation, and then you solve for the roots. Okay, after you get your roots, you just use the formula. Here we are in the case of 2 distinct real roots. So the solution looks like e to the r1x and e to the r2x. Okay, and now because we have initial value, all right, so we can actually plug in the initial value and figure out c1 and c2. So let's plug in y of 0. Y of 0 is 1. Okay, so we plug in it, c1, when we plug in x is 0, we get 1, c2, e to the 0 is also 1. We get one equation about c1 and c2. To get the second equation, we actually need y prime. Okay, so the derivative of e to the 5x is e to the 5x times 5. Derivative of e to the 3x is e to the 3x times 3. Okay, we plug in y prime of 0, and that is 3. So that is 5c1, e to the 0 is 1, plus 3c2, e to the 0 is also 1. Okay, now we have 2 equations. We should be able to find the unknown, right? Okay. Remember, we want to find C1 and C2. The first equation, we have this. C1 plus C2 is 1. Second equation, 5C2 and 5C1 plus 3C2 is 3. Okay, how do we solve? Well, use negative 5R1 add to R2. Okay, so 1 stay there. 5 minus 5, 0. 3 minus 5, negative 2. 3 minus 5, negative 2. Oh, so this is the coefficient of C1. This is coefficient of C2. That is the right-hand side. What does the last row tell us? The last row tells us minus 2, C2 is C2. So what is C2? Yes, 1. And the first, what is the first? So the first one, we plug in the first equation, C1 plus C2 equals to 1, but C2 is 1, so that means C1 is 0. So actually, according to our initial condition, we will get the solution y is C1 is 0, and then C2 is 1, so it's just e to the 3x. So that is our solution in this example. So far, so good, everybody? Okay. That is the first case when we have 2 real roots. What is the next case? What happens when we have a repeated real root? Okay. All right. So let's see. Okay, so we just repeat the process, right? And we get this is the characteristic equation, okay? But here, because the discriminant b squared minus 4ac is 0, so this term is actually gone, okay? And then we have minus b over 2a, that is our root, okay? That's our roots. Okay, and so unlike the first case when we have 2 distinct real roots, the solution is like y is e to the r1x, that's y1, y2 is e to the r2x. But here we only have one root, so that's why we must have like e to the r1x, but we also need another one. How do we construct the other one? Oh, we cannot use the same thing, right? But you think about what functions that when you take the derivative, that we will get e to the r1x. Okay, well, put an x here. Okay, then when you take the derivative, you will actually get something like e to the r1x. Okay, so that is why for one repeated real root, the first solution is e to the r1x. The second solution is x times e to the r1x. All right. Next. Are they linearly independent? Okay, so let's see. Let's check. Okay, so we have the first solution and the second solution. All right. Oh, by the way, I forgot to show you why this is actually a solution. So why this guy is actually a solution? Let me show you. Okay. Yeah, sometimes I forget things. Sorry. So how do we show this guy is a solution? Well, we need y2 prime. What's the derivative? It's the product rule. X prime is 1, and then the second guy plus x, the derivative of the second guy. Okay. And then we also need the second derivative. Here, product rule again. Okay, so x r1 prime is r1 times second guy plus first guy, derivative of second guy. We have extra R1. Oops, extra R1 is right here. Okay. And so here, that's why we get R1 squared, okay? So this is R1 squared. So that's why when we plot this into our original differential equation, we get a y prime prime is all of that. Let me multiply out. So e to the r1x, a r1 e to the r1x, a xr squared e to the r1x, okay, plus b times y prime. So b times y prime is e to the r1x. I also distribute it. X e to the r1 e to the r1x plus c times y. So c times x e to the r1x. Okay, what is that? Let's see. We can group all the. Hey, how come I have it? So here, this is r1. Okay. So you can see we can combine the like terms. What are the constant term? The constant term is this guy. Okay, so that is let me put it down here. Okay, so the constant term is a e. So let me also combine the like terms. So it's a plus b e to the r1x. And then what's the next term? Let me change the color to indicate. So next term we have the x, right? Let me see. Do I forget something? Okay. All right. All right. Let's see x. Oh, I see that I forgot one thing. I forgot a vector. So I also forget, oopsie. I also forget this one. Okay, so that's why those are the terms of e to the r1x. So I have a and I have so we have a and we have a r1 and we have b. Okay, so that and plus plus, and then we can factor out x e to the r1x. What do we have? We have a, okay, we have a, oh, so here this is r1 squared. So we have a r1 squared plus b. So this term, b r1, okay, and the c as well. So c, okay. So now what happened? Okay, so what happened here? Oh, I find my mistake. Okay, so my mistake is here. When I take my derivative, okay, this guy I forgot to multiply by r1. Okay, so this one we should have r1 here. Okay, so here we should be a times r1. So we have 2a times r1 here. So 2a r1 plus b. This is it. And what is that? Remember that r1 equals to negative b over 2a. So it means negative b equals to 2a times r1. So 2a r1 plus b is actually 0. So that's why we get 0 for this guy. Okay, this guy is 0. And then plus this guy is also 0. Right, because r1 satisfy the characteristic equation. So yeah, we actually get 0. So this guy is actually a solution of the differential equation. Okay. All right. Okay. So All right, so we get two solutions, and how do we check whether they are linearly independent? So we find the derivative of them, okay, and then we do the determinant of this one skin, okay? So cross multiply e to the r1x times this guy. You will see the difference is you actually get 2 copy of r1x in the exponents, and e to the r1x times e to the r1x is 2 copy of r1x in the exponents. And then subtract r1x times x and e to the 2r1x. So you can factor out, you can see this guy and this guy cancel. We only have e to the 2r1x. And that's the exponential term is not equal to 0. Okay, so those two solutions are actually linearly independent. Okay, and then we can also set the augmented coefficient matrix to find the constant C1, C2 given the initial condition. Okay, so let's continue with this example. Okay, all right, so let's see. First of all, I don't like to see fraction in the coefficients. Let me multiply by 5 for all the terms. Then I have 25 y prime prime minus 30 y prime plus 9 y equal to 0. Okay, so what is the characteristic equation? Whenever you see y prime prime, we place that by r squared. Whenever you see y prime, we place that by r. And for the y, you just put a constant 9 there. Okay? So that is the characteristic equation. Do you realize 25 is actually 5 squared and 9 is 3 squared? And 30 is 2 times 3 times 5. So this guy is actually 5r minus 3 complete square. So we get a repeated root. R is 3 over 5. Okay? And then after you get like the repeated roots, our solution is just C1 e to the 3 over 5x plus C2 x e to the 3 over 5x. Okay? That is our solution. And then we can plug in the initial condition to figure out C1 and C2. Okay, let's do that. Y1 is 0. So when we plug in 1, we get C1 e to the 3 over 5 plus C2 x is 1, so e to the 3 over 5. X is 1. Okay. All right. Okay, my computer freeze. Let me wait a little bit.